Hello everyone, and welcome to today's webinar, which is titled Subject-Specific Lower Limb Modeling and Evaluation with a Force-Dependent Kinematics Natural Knee Model. My name is Christopher Iversen, and I'm from Anybody Technology, and I will be the host of today's webinar. And today I am here with my colleague Søren Tørholm, who will be helping with the Q&A session in the end. So today we have an external speaker who is David Leandro Dejtiar, who has a master's degree in sports technology from Aalborg University here in Denmark. And David is going to give his presentation in a minute or so. But just before we start, I will give a general introduction to the Anybody modeling system for those of you who is unfamiliar with the software or musculoskeletal modeling in general. So the Anybody modeling system is a software that allows you to do musculoskeletal modeling. As input, it takes motion data as kinematics and forces, and it calculates the internal body loads as joint moments, joint reaction forces, and muscle forces. And right on the bottom of the screen, you can see a screenshot from the Anybody modeling software. So this is actually how it looks. So right now, Anybody is used in a wide variety of areas and applications. And a few examples of this is movement analysis, product optimization design, the sports field, orthopedics and rehabilitation, and assistive devices. And the typical workflow in the Anybody modeling system could look something like this. So you provide the motion data as input and use the body models which you or others have built. And then you provide some kind of environments. It could be something like an exoskeleton. Then you can use the Anybody modeling system to combine these things and then run the inverse dynamics and calculate the muscle recruitments. And then you can calculate the internal body loads as muscle forces and joint moments. You can then use the results to do some post-processing, for example, using some finite element tools. But a lot of users also closes this loop by optimizing that design in some way and running this loop again. So this brings me to the end of this introduction, and I'll give the word to David instead. So I will just make you the presenter, David. Yes, so we see your screen, yeah, and we are looking forward to hear your presentation.
Perfect. So yeah, thanks, Christopher, for the introduction, and good afternoon, everyone. On today's webinar, we will talk about a project developed during my stay at Aalborg University, although I am part now of the Ground project funded by the European Union at the Universidad of Zaragoza and Materialize. Today, I will give a brief introduction on the relevance of natural subject-specific models for certain applications, followed by explaining how did we construct these models. Then we will go through the evaluation of the model predictions compared to experimental measures. To conclude, we will discuss some implications and limitations and comment on a clinical application for a natural subject-specific model. So, as Christopher said, musculoskeletal models are great to estimate what cannot be easily measured, as it could be muscle activation and force in sports, contact forces in ergonomics, joint loads with exoskeletons, or the effect of orthopedic devices. And one way to build these models is by using the model repository, where we have pre-made models that can be easily adapted to your needs. But what about the scaling? So how can we take into account the differences between subjects? One method, the simplest one here, is linear scaling here on the left, where we just use a mass length relation to scale everything by a factor. Another one, straightforward to use in anybody, is the kinematical scaling, where we can optimize some anthropometric parameters to fit experimental data. Although none of these methods take into account geometrical differences such as deformities. So it has been previously demonstrated that subject-specific geometries greatly improve predictions of joint contact forces and ligament strains. The tool that we have available to view the 3D geometries of patients are computed tomography, or CT, and magnetic resonance imaging, or MRI. Therefore, the process here is to start from medical images and end up with a subject-specific musculoskeletal model. Such personalized models have been previously developed, although most of the evaluation efforts have been made with patient models incorporated and instrumented total knee replacement, like the one developed by Marco Marra and colleagues that won the 5th Grand Data Challenge. However, for certain applications, we also require natural joint models, which need to be reliable, and therefore we must evaluate these models on their own. Knowing that, we specified the main objectives of this study as first, to develop a detailed natural knee model incorporating subject-specific geometries that can be driven by motion capture, and second, to evaluate the model performance with bilateral X-ray images. Jumping into the materials, what we required to perform this study were magnetic resonance images from the lower limb, plus detailed images of the knee following the osteoarthritis initiative protocol. We also recorded our subjects performing lunges with optical motion capture and a forced platform under the front foot. And with the purpose to evaluate the models, we did also take B-plane X-ray images of the subjects performing lunges in a different experimental session with the EOS system. If you go step by step over the methods, we first had to segment the magnetic resonance images manually. We segmented pelvis, femur, patella, tibia, and talus, and then the foot was also segmented as only one full segment, including all the bones of the foot. The contralateral femoral head was also segmented in order to specify the pelvis width. With the masks done, we could reconstruct these 3D geometries of the patient's bone. Until here, this process was entirely done in the Mimic software for Materialize. Next was to include the subject-specific bones into our model. For that, we took the source bones used in any body. They correspond to the 20 lower extremity model, which include muscular attachment points and our segmented bones, and to morph our segmented bones. For that, we first aligned the source bones, so the green ones here on the picture of the right, to the segmented ones, the red ones on the picture. Using our inertia axis alignment, we aligned those ones, and then we morph the source mesh to the segmented one, and therefore scaling the muscle attachment points. We moreover defined joint centers and axes in Freematic, also a software for Materialize, in order to define based on some landmarks. Once we had our subject-specific bone models, we could already run an inverse kinematic analysis with idealized joints. For that, we started performing a multi-body kinematic optimization, where we use the recorded trajectories of optical markers attached to the skin to drive our musculoskeletal model. At this point, the model had 3 degrees of freedom at the hip, 1 at the knee, 1 for the patella, and 2 in the ankle, all formed by idealized joints. Although if we want to further investigate the secondary joint movements in the knee, like internal, external, or valgus valgus rotations, we cannot use an idealized joint as this one, with only 1 degree of freedom in the knee. To include this detail of representation of the knee joint, we needed to segment the detailed magnetic resonance images, from which images we could extract the ligament attachment points together with the contact surfaces which correspond to the cartilage surface. If we include all this in our model, meaning ligament, muscles, and contact surfaces, we end up with our definitive model, as here pictured. In here, the ligaments were modeled as non-linear elastic elements between the attachment points previously selected. The contact forces were based on an elastic foundation contact model, and the muscles, which attachment points were selected during the morphing process, were modeled as a three-element heel-type string muscles wrapping over the bone surface. A third-order polynomial cost function was used to minimize the cubed muscle activations in order to solve the muscle recruitment problem. Then, all that is left is to solve the force-dependent kinematic analysis. Explained briefly, in this force-dependent kinematic knee joint model, we remove the existing revolute joint, so this idealized 1 degree of freedom joint, and replace it with 11 degrees of freedom, which correspond to 6 degrees of freedom in the knee, where we only drive the knee flexion angle from the previous kinematic optimization, and 5 for the patella, as the patella tendon was modeled as rigid. In a force-dependent kinematic analysis, we take into account the muscle, ligament, and contact forces, and try to balance these ones inside the FDK solver. As a brief recap of what we did so far, we first segmented the medical images and morphed the model. Then we defined joint axes and centers based on bony landmarks. With that, by using the recorded marker trajectories, we could already perform the multi-body kinematic optimization. Then we had to define the contact ligament, and muscle models, which required to perform a force-dependent kinematic analysis. To evaluate the model, we used measures of rotations and translations reconstructed from biplanar X-ray scans. The X-ray scans were taken with the EOS scanner, which allows to take X-ray images at weight-bearing positions. From the bilateral X-ray images, we could reconstruct the three-dimensional positions of femur, tibia, and patella by projecting the contour of the segmented geometries and register it to the contour of the X-ray images. Then we use anybody to calculate the positions and orientations of femur, tibia, and patella in the 3D space. For the evaluation of the model, we compare the kinematics estimated during the force-dependent kinematics analysis to the knee joint kinematics reconstructed from the X-ray images at the specific knee flexion angles. Here at the right, you can see the kinematic graphs, where each color is one subject. The dots are the measures reconstructed from the EOS experiments, and the lines the model estimations, with the shaded area as the standard error. In general, between all the models and measures, we found an absolute mean error of 2.13 millimeters and a bit below 9 degrees for rotation. These results are indeed well inside what has been previously reported with similar models. If we look into the knee ligament forces estimated, we see that they are highly dependent on the subgroup-specific geometries and even on the trial, where we see large differences inter and intra-subject. We did not evaluate ligament forces itself, first because the measurements will require an invasive approach, and second, because at the time of this project, we did not find literature reporting knee ligament forces or elongations during a lunge. From our experience, we can also say that knee kinematics and ligament attachment points, and even the ligament parameters, meaning the stiffness and reference strain, have a large influence in the knee stability. If we look into the contact forces, we can see that our model reported slightly larger joint loads than previous studies, although the trend follows the same as measured during the squats with instrumented knee replacements. One reason to explain these high contact forces and ligament forces might be the muscular force, which we did not evaluate. In a force-dependent kinematic analysis, where we balance the joint contact forces, ligament, and muscles, it could happen that all the forces are under or over predicted, although the trend should stay stable, as we can see here and compared to other studies as well. Approaching the conclusion of this project, we can discuss that secondary knee joint kinematics are not mere functions of knee flexion angle. They depend on the subject geometry and knee stability. Although there have been successful inventions to estimate in vivo subject-specific knee stability, models in the literature do not incorporate such level of detail, and ligament parameters are based on cadavers experiments reported in the literature. Although in other models, we incorporate ligament attachment points extracted from the medical images, it has also been demonstrated by Michael Skipper Anderson that small differences in attachment locations can lead to large differences in model estimations. In this regard, we did not optimize ligament parameters or attachments to improve the kinematic estimations. For one subject, indeed, we had to increase a bit the pre-strain of the medial collateral ligament in order to help the force-dependent solver find a solution. In conclusion, we developed a powerful tool to simulate force-dependent knee behavior on an individual level. We evaluated the model estimation and force and found a good agreement in estimations and experimental measures. And we believe that this method could be really useful to optimize clinical treatments, for which I will show an example of a clinical application. So in this application is what I'm currently working on. It's part of my PhD project funded by the European Union Horizons 2020 program, where I work at Materialize with the Universidad de Zaragoza as my doctoral school. Here I will explain the tool that we are developing to optimize the implant position in total knee arthroplasty. So first of all, what is a total knee arthroplasty and why is it so important? Well, total knee arthroplasties are surgical procedures done to knees with end stage of arthritis, where drugs and physiotherapy do not provide a solution anymore. In these cases, the knee joint is replaced by a prosthesis. Total knee replacements are commonly performed, and the numbers are bound to increase with the aging of the population. Although total knee arthroplasty is a common procedure, reports of about 20% of dissatisfactions are reported in the literature. Reasons might vary between anterior knee pain, instability or stiffness, a limited range of motion, or a subjective feeling of abnormal walking. On the other hand, when the surgeon approaches a total knee arthroplasty procedure, he finds himself facing multiple surgical options. For example, the alignment to use for the position of the implant, with the most common one is following a mechanical alignment, as shown here on the right, where the aim is to achieve a straight hip-knee ankle line. There are other alignment options, like kinematic alignment, that attempts to restore the natural joint line. Other options include the prosthesis type, being a posterior stabilized with a posterior cam mechanism or a posterior cruciate retaining that maintains the posterior cruciate ligament. But there are many others in the market. There are also different techniques to balance the knee intraoperatively in flexion and extension, as it could be like gap balancing or soft tissue balancing. For our project, we will only focus on optimizing the alignment with a cruciate retaining implant. Then, the specific goal of this project is therefore first to simulate a patient-specific knee based on magnetic resonance images used to plan the surgery, and also with the implant in a post-total knee arthroplasty model. A second objective is to develop a tool which will allow us to modify the implant position that will result in the closest post-total knee arthroplasty kinematic to the natural knee. The workflow will therefore look something like this. First, we'll simulate the native knee model and obtain an estimation of secondary joint kinematics, ligament strains, or contact forces. Then we will incorporate the prosthesis in the model in a predefined mechanical alignment and estimate the results again, which will result in a different kinematics, for example. Afterwards, we will modify the implant position within a range to try to find an optimal implant position that will result in the lowest difference between native kinematics and post-total knee arthroplasty kinematics, for example. For this project, we use a different model, which is somehow a simplified version of the one that we just saw. It also contains an 11-degree of freedom knee joint based on geometries extracted from magnetic resonance images. Although we did not morph the 20 lower extremity model as previously, and instead defined manually the attachment points of the three muscles that we use, the quadriceps and two for the hamstrings. Similar to the previous model, we also drive the knee flexion angle. The original version of this model was developed by Valentin Manhuele, and I believe there is also a webcast of it in the Anybody YouTube channel. We evaluated the model against optical motion capture for 7 specimens. The experiments also recorded ligament strains at the lateral collateral and medial collateral ligaments, although we are not using that right now. And as previously, are based on detailed magnetic resonance images of the knee that we recorded with the same protocol. The evaluation of the model with the recorded kinematics resulted in average root mean square errors of 2.28 millimeters for translations and 2.21 degrees for rotations. The next step to reach our goal, we require to perform multiple simulations with different implant positions. To do this, we use the any PyTools model to automatize the simulations from within the Python environment. We then use our antibody knee model to train an artificial neural network with 1,800 samples at different flexion angles and with random implant positions, random implant combinations between a given range. The neural network then learned the relationship between the implant position and the estimated kinematics in order to find the implant alignment that results in the smallest mean square error between native values and post-total knee arthroplasty values. This is work currently under development, but to give you some preliminary results, at this point, we could effectively approach native kinematics with small variations of implant position with respect to the initial mechanical alignment shown here on the right. In this graph, the black dotted line are experimental values, and the blue is the initial alignment with the mechanical alignment, where the orange line it's the optimized values that our artificial neural network could find. We see that only the internal external kinematics remain with large differences, although it is a pattern that we also see with custom patient-specific implants. That's all what I wanted to say today. Thanks you very much for your attention, and I will be happy to answer some questions.
So thank you very much for the presentation, David. I'll just take the presenter role back here. Yeah, so just before we go to the Q&A session, we will just have like to say a few words from the Anybody's Technology sites. So we would also like to acknowledge the CPR, the Danish Council for Independent Research, IOI, and the Innovation Fund Denmark, and of the Anybody Research Project. We would also like to point your attention to the anybodytech.com, where you can go and find some events and special dates, and you can also find the full publication list we're using the Anybody modeling system. You can also check out anyscript.org, where we have the wiki page, and we have all the repository page, and where you can meet some fellow Anybody users at the forum. Then I would like to also point your attention that we have a webcast tomorrow, which is also a presentation by David on force-dependent kinematics natural knee model presentation. But this time we'll try to do it in Spanish instead. And if you have any question towards anybody or the Anybody modeling system in general, or you want to meet us, then please send an email to sales@anybodytech.com, and we'll be happy to set a meeting up with you. And then finally, it's time for some questions. So I will be reading some of the questions for you, David, and then you will be able to answer them.
Okay, perfect.
Yeah. So the first question we got was, do you think that a knee laxity test such as Lachman or else could help to enhance the ligament models?
Well, that's in specific that you mentioned. I don't believe so, because they are highly subjective, and it's hard to include them as an objective measure. There are other ways to include site-specific laxities. I believe there is an invention by Dennis Pedersen which take into account these laxities or try to optimize these laxities, but in a more complex way, using also the EOS system and a force platform. Hope that answers your question.
Yeah, I think so. So another question we got was the models, the muscles you modeled. Was the muscles modeled as simple muscles or 3D hill models?
They were modeled as three element hill type models.
Okay, and how was these muscles calibrated? Is it some kind of customized calibration or the default calibration?
It was the default calibration, and we used the mass to solve the muscle requirement problem. We used this cubic polynomial function.
Yeah. So quickly moving on to another question. So ligaments were modeled using a linear approximation. Do you think non-linear approximation would impact significantly of the FTK findings?
I believe so, because I think so that the ligaments have a huge role here. We did use the ligaments as described by Blankenburg in a paper from '91. Where we do have a slack region, then a polynomial 2 region, and a linear strain region for higher strains. I do believe that the ligament model and also the wrapping surface of the ligaments and even the ligament parameters play a huge role in the kinematics. For this case, we used what was previously done, and we were able to find good agreement.
Yes, thank you. So I'll just look through all the questions here. So one other question was, why did you not morph the foot like all the other bones?
Yes, first of all, because from the MRI images, some part of the foot was missing, so like the toes of the foot. And then as the foot was static on the ground, it was easier for us just to use an affine transformation based on some landmarks to scale the foot linearly.
Okay, so we are getting a lot of questions, David. So I think that that will be all for the Q&A session now, and then I'll send the questions for you, and we can answer them all by email. So yeah. So
nice that I ended up earlier.
So don't be afraid. We'll answer all of your questions, and I'll send them to David right after this webinar. But thank you very much for the presentation, and thank you for everyone who was listening in. And once again, please feel free to send us an email or message on LinkedIn or through our email if you want to know more about the Anybody Modeling System or you want to get in contact with us. Then I just want to say thank you for today, and yeah, one last time, thank you for the presentation, David.
Thanks to you. Thank you very much.
Thank you.